Good day everyone. So for today's lecture, we will discuss first condition of equilibrium. We will now solve problems for the first condition of equilibrium in three-dimensional force system. So let's answer this problem. So determine the tension developed in cables AB, AC, and AD in this diagram. So as you can see, we have three chords. So we have here, this is the chord between AB, this is AC, and AD. Now, if there is another chord, usually this one, which is the 900 Newton, which is usually this is the weight. So, if that is the case, so we will name this one as another force or another tension. So, let's identify first the tension or the forces on this diagram. So, I will call this as my T1, and the direction of that is going down. This is now my T2, and that is along positive X. This is now my T3, so that is along positive Y but negative X. And this is my T4, that is along negative Y and positive Z. So now, since we already identified these forces and we have forces that are in between octant, so that is T3 and T4, we will now get their components. So let's solve the angles here since there are slopes here. So let's get first this angle. So let's call that as theta, and based on this slope, so that is 3 over 4. So if this is theta, that is 3 over 4, and that is theta is 36.87. While for T4, the angle of this, so we will call this as phi, so that is 4 over 3, and that is 53 degrees. Let's draw this in a free body diagram. So my T1 again is going down. So since this is along negative Z axis, so there are no components needed. T2 is along positive X. Well, for T3, I have to draw it like this since T3 is between Y and negative X. So I have here T3Y, which is positive, and T3X, which is negative. So here for T4, I have the components which are T4Y, that is negative Y, along negative Y, and T4Z, which is along positive Z. So let's try to solve this problem. So we have to note this is three-dimensional. So forces along X, forces along Y, and forces along Z. So let's start with the forces along X. So the forces along X is equal to 0, and let's identify what are the forces along X here. So we have positive first. So we have T2. So that is T2. Then we have here another one, which is negative T3X. That is negative because that is along negative X. And that is equal to 0. Since this has components, so we will get the equivalent of this. So that is T3X. This one is also T3X. So that is opposite of theta. So we will use a sign. So this T3X will be equivalent to minus T3 sine theta is equal to 0. Okay, based on the given, T2 is unknown. Okay, we don't know T2, and we also don't know what is T3. Since there are two unknowns, we cannot proceed here. So let's solve for the summation of forces along Y. So the summation of forces along Y equal to 0. And how many forces do we have along Y? So we have here T3Y and T4Y. Okay, so T3Y is along positive Y, while T4Y is along negative Y. So we will have T3Y first. So T 3y, that is positive, minus t 4y, that is negative, and that is equal to 0. Since both of them have subscript, we will get the equivalent. So t3 is the adjacent of theta, so that will be cosine. So t3 cosine theta. Then for t4, that is also the adjacent of phi, so that is minus t4 cosine phi is equal to 0. So again, we don't know what is t3. We also don't know what is t4. So we cannot proceed on solving this one. So the summation of forces now on Z is equal to 0. If we will check, how many forces do we have along Z? So we have T4Z, that is positive, and T1. So let's write first T4Z, that is positive, then minus T1 is equal to 0. Since T4Z have subscript, so let's replace T4Z into, so if we will look, so this is phi, and this is T4Z. So T4Z is this one. So this is T4Z, and that is opposite of phi. So it means that is T4 sine phi minus T1 is equal to 0. And if we will check the given, we don't know what is T4, but we know T1 and we know phi. So we can solve now what is T4. And let's derive this one. So T4 is equal to, that is T1, then divide both sides by sine phi. So that will be, T1 is 900 Newton, while sine phi is sine 53.13 degrees. So the answer for T4 is 1,125 newtons. Now, since we know T4, let's see which one can we solve. I think we can solve T3 here because we know T4 in this equation. So let's derive this one. We can solve T4 here. So since T4 is negative, so I have to transpose T4 on the other side. So that will be T3 cosine theta is equal to T4 cosine phi. And divide both sides by cosine theta so that I can find T3. So that is T3 is equal to T4 cosine phi divided by cosine theta. And let's substitute now the given. So the given are T4 based on our solution answer for T4, that is 1,125 Newton, cosine phi, that is 53.13 degrees, divided by cosine theta. Cosine theta is 36.87 degrees. So T3 is 843.75 Newton. So this is now our T3. Okay, so let's solve now T2 since we know what is T3. So I will just transpose T3 on the other side. So it will be T2 is equal to T3 sine theta. And our answer for T3 is 843.75 Newton. Sine theta is sine 36.87 degrees. So T2 now is 506.5 6.25 Newton. So this is now our T2. This time, let's solve this problem using what we have learned before in Cartesian vector. So it means we will represent our each vector into this form in which a force is equal to Fx I hat plus Fy j hat plus Fz k hat. So it means my T1 here, it will be T1x I hat plus T1y j hat plus T1z k hat. Same with T2, same with T3, and same with T4. Okay, so if you will look here, our T1 is directly along z-axis. So I can say here, okay, so my value for my T1 here is equal to, so my T1 here is 900 Newton k hat. But since my T1 is directly on negative z, so it means this is negative 900 Newton k hat. Okay, because it has no x component, no y component, it has only z component. While for T2, so for my T2, it is directly along x only, and but this time we don't know the value, so we will just have our force vector T2, we will just write T2. Okay, so this one is a force, so I will write here T2, that is the magnitude, and since that is along positive x, so I will write here as I hat. Okay, so again, so this is a force vector, this is a force vector, and this is a magnitude. Okay, for T3, so for T3, we will use what we have learned before. So since we have an angle here, okay, so to determine what is T3, so I will just have here T3, the magnitude, times its unit vector. Okay, so it came from our formula, which is, so if you remember our formula for force, the other formula for force to get this Cartesian vector form is what is the magnitude times unit vector. Since we don't know what is unit vector, so I just write here the magnitude of T3 times its unit vector. What are the solutions we can use to find the unit vector? So we know that the unit vector can be found by the Cartesian vector f divided by its magnitude. But since we don't know what is the magnitude, we cannot use this one, the first formula for our unit vector. What we're going to do is we have to use this, okay, in which unit vector is equal to cosine alpha I hat, cosine beta j hat, and cosine gamma k hat. And remember, alpha, beta, and gamma angles are angles coming from their positive axis. Okay, so if we will look here, so this is now our T3. Okay, so this is positive x, so this is our positive x, so the angle of this is coming from, the alpha of this is coming from positive x going here, so it will be 90 degrees from theta. So I will write it here. So to get the unit vector of T3, so my alpha is equal to 90 degrees plus theta, and from our solution, theta is 90 degrees plus 36.87 degrees, so alpha is 126.87 degrees. So that is for our alpha. For beta, that is the angle from positive y going here, so this is beta, and that is also our theta. So beta is also equal to 36.87 degrees. While for gamma is this one, so that is from positive x going to our vector, so that is equivalent to 90. So our gamma is equal to 90 degrees. So if we will now compute for our unit vector, so that is unit vector, okay, of T3, it will be equal to cosine alpha I hat plus cosine beta j hat plus cosine gamma k hat, and that will be, so cosine 126.87 degrees I hat plus cosine beta is 36.87 degrees j hat plus cosine 90 degrees k hat. So let's solve for the unit vector. So that will be cosine 126.87, so that is equivalent to negative 0.6 I hat. Cosine 36.87, so that is positive 0.8 j hat, and cosine 90 is 0, so this is now our unit vector. So for T3, our T3 is equal to T3, and the unit vector is this, negative 0.6 I hat plus 0.8 j hat, and that's it. Now if I will distribute T3, so I can also write this as negative 0.6 T3 I hat plus 0.8 T3 j hat. Okay, so for T4, it is equivalent to, since the magnitude is still unknown, so T4, then the unit vector u. So same, we have to use this formula. The u is equal to cosine alpha I hat plus cosine beta j hat plus cosine gamma k hat to find the unit vector and to find the force vector T4. So for this, so let's look on T4. So what is the angle of this vector to positive x? So that is definitely 90. Okay, so here alpha is 90 degrees. While for positive y, what is the angle of T4 from positive y? So this is positive y going to T4. So I can say that is 90 degrees plus this one, this angle. So that is 90 degrees plus this angle. So if this is phi is 57.13, so this angle is 36.87. So my beta now is equal to 90 plus 36.87. So it will be 126.87 degrees. While for my gamma, coming from positive z going to my angle, so this angle is 36.87. So gamma is 36.87 degrees. Okay, so if we will now solve for the unit vector, so that will be u. So this is the unit vector of T4, so that is cosine 90 degrees I hat plus cosine 126.87 j hat and plus cosine 36.87 degrees k hat. Okay, so if we will now solve its unit vector now is cosine 90, that is 0. So there's no component on I hat. Cosine 126.87, so that is negative. So that is negative 0.6 I hat. Then cosine 36.87, so that is 0.8. So plus 0.8 k hat. And let's now substitute it to T4. So the force vector T4 is equal to T4, its magnitude, times the unit vector 0.6 j hat plus 0.8 k hat. And let's distribute that one. So that will be negative 0.6 T4 j hat plus 0.8 T4 k hat. So this is now our force vector for T4. Okay, so what is the next step in solving this one? So we know that the summation of forces is equal to 0. So it means I have to add all the forces. So the forces are equal to 0. So that will be T1 plus T2 plus T3 plus T4, which is equal to 0 because they are in equilibrium. T1 is negative 900 Newton K hat. T2 is positive T2 I hat. T3 is negative 0.6 T3 I hat plus 0.8 T3 J hat plus this T4 is negative 0.6 T4 J hat plus 0.8 T4 K hat, okay, which is equal to 0. Now for this, we have to get all the forces on X. So from this equation, so what are the forces on X? So this is equal to 0. So the forces are this. So we only have 2. So this is T2 I hat minus 0.6 T3 I hat. So that is T2 I hat minus 0.6 T3 I hat is equal to 0. Since we don't know what is T2 and we don't know what is T3, so we cannot solve anything here. So let's solve for the forces along Y. So that is also equal to 0. So the forces along Y, so we have here and this one. So 0.8 T3 J hat minus 0.6 T4 J hat is also equal to 0. But we don't know what is T3 and T4, so we cannot solve anything from Y. And let's solve for the forces along Z. So we have here, how many forces do we have along Z axis? So that is equal to 0. So we have 2, this one and this one. Okay, so that will be negative 900 Newton K hat plus 0.8 T4 K hat is equal to 0. So from this, definitely we can solve what is T4. So that will be 0.8 T4 K hat and transpose the 900 Newton on the other side. So that is equal to 900 Newton K hat. Then divide both sides by 0.8 K hat. So that is 0.8 K hat. So that will be T4. So this is cancelled out. T4 now is equal to 900 Newton divided by 0.8. So T4 is equal to 1125 Newton. So this is T4. Now, since we know T4, if we will look on here, on forces along Y, we can solve T3. So I have to transpose negative 0.6 t for j hat on the other side so that it will be positive. So that will be 0.8 t3 j hat is equal to 0.6 t4. This is j hat. Since we know what is t4, let's solve t3. So divide both sides by 0.8 j hat and 0.8 j hat. So cancel the j hat. So it will be t3 is equal to 0.6 t4 divided by 0.8. And let's substitute. So that will be 0.6 t4 is 1125 Newton divided by 0.8, and t3 now is equal to 843.75 Newton. So this is now our answer for t3. Since we know what is t3, we can now solve for t2. And to solve t2, it will be just, since t2 is positive, so I will just transpose negative 0.6 t3 I hat on the other side. So it will be t2 I hat is equal to 0.6 t3 I hat. Then divide both sides by I hat. So it will be cancelled out. So t2 is now equal to 0.6 t3. And point t3 is 843.75 Newton. So that will be t2 now is equal to 506.25 Newton, which is the same from our previous solution. Okay, so this is now another solution for solving t2, t3, and t4. So I hope this is clear.